Hello, everyone, and welcome to this panel discussion on safe and responsible reuse of wastewater resources. This webinar is co-organized by the Environmental Science Curriculum Series and the EcoRisk 2050 Innovative Training Networks. My name is Marlene Ågerstrand, and I am an assistant professor at the Department of Environmental Science at Stockholm University. I will be serving as the moderator for the webinar. I would like to start by giving a quick overview of the schedule for today. In a moment, I will introduce our three panelists, and they will have each around 10 minutes to present about issues pertaining to reuse of wastewater resources in their respective regions. Thereafter, we will have a 25-minute panel discussion, and finally, there will be 15 minutes for audience Q&A. You are all welcome to pose questions at any time during this webinar, and please use the Q&A bottom somewhere here on your screen. And with that, it is my great pleasure to introduce our panelists. First, we have Professor Annemarie Van Vezel. She is the Scientific Director at the Institute for Biodiversity and Ecosystem Dynamics at the University of Amsterdam. She's also a member of the Dutch Health Council and the Dutch Board on Authorization of Plant Protection Products and Biocides. Her research focuses on water quality, risk assessment and risk mitigation, environmental toxicology and chemistry, and environmental policy evaluation. Welcome, Annemarie. Second, we have Professor Benny Chefetz. He is the Dean of the Faculty of Agriculture, Food and Environment at the Hebrew University of Jerusalem. His research focuses on the fate of organic molecules in the environment, with a particular interest on the agriculture irrigation with reclaimed wastewater and the effects on human health. Welcome, Benny. Last but not least, we have Anders Vinson. He is the coordinator for European Affairs and a senior environment advisor for the Swedish Water and Wastewater Association. His expert fields are control at source strategies for hazardous chemicals, circular economy, wastewater treatment processes, and energy and biogas production. Welcome, Anders. Panelists, thank you all for taking the time to be here today. I will start by inviting Annemarie to present her opening remarks.
Thank you, Marlene. It will be a pleasure. If all is right, oops, you can see now the screen. So I will talk today about intentional water reuse as compared to the non-intentional water reuse, which very often occurs. And a substantial part of the work that I'll present today, Dominique, is also based on the work that Dominique Narijn-Fort is doing for her PhD work. Well, if we are talking about responsible water reuse, we should keep in mind that different disciplines are needed for this. So, of course, we have to know about what's the water demand, what's the availability, what's the type of reuse application. Very important, and we'll talk today about that. What are the health and safety consequences of the water reuse? What can we do to mitigate risks, for example, by treatment technologies? And of course, also governance is of importance, because water, especially maybe in the Dutch context, where our water boards are the oldest policy structure that we have, is always related to issues of governance. When we look in this wet country where I live in, the Netherlands, the current practice, and I think in many EU countries still, is that we do reuse water, but we do it in an uncontrolled, not always intentional, and also indirect reuse way, which means that we don't think about, well, what stakes are here at risks, We don't include proper treatment technologies, and it might also be inefficient. So I think it's very good to really be aware about all these types of possible problems so that we can also look at the solutions, so that we can go to responsible water reuse. Of course, in the European context and also internationally, there is a lot of legislative frameworks for water reuse, both for industry, for agriculture, and for drinking water. Here you see a whole list, but in not too many of them there are explicitly quality criteria set for chemicals of emerging concern or for pathogenic microorganisms. As you know, there is now the EU legislation on water reuse recently has been developed. Well, what we are thinking of in the Netherlands is to include subsurface irrigation systems, and you can see this picture here. You have an agricultural field, in this case a maize field. There is a sewage treatment plant in the neighborhood, and in fact the same systems as are being used for drainage are also being used for irrigation. So it's below soil, within the groundwater, below the groundwater table, and well, when we have this subsurface irrigation, then also the groundwater table is rising. And this subsurface irrigation system serves a dual purpose, both to supply, of course, the water to the crops, but also to have the soil being used as a kind of filter to clean the water, so that the water, which is won't go directly to the surface water, the effluent, which is normally does, it goes again to the surface water, but being cleaned. We have a real scale project in the Netherlands, in Haaksbergen, where we do this. So we have the direct domestic wastewater reuse. And it's an intentional system compared to the de facto unintentional irrigation that is much more often used in the Netherlands. Well, if we compare these different irrigation systems, here you see the subsurface, you see the drip irrigation system, and also the sprinkler irrigation system. We expect that especially both sorption and transformations will much more happen in the subsurface irrigation system compared to the other many used irrigation systems, which are basically normally surface irrigation system. And this table comes from a review by Dominique, which was published in 2020. So we do this on real scale. So here you see the site with the sewage treatment plant. Here you see the site where we have this subsurface irrigation, and here we have the comparable site, the same type of soil, the same type of, it's in fact from the same farmer, but it's not irrigated. And also during these last 3 years of very, very dry summers, you can very well see the difference between the fields with crops being much greener than on the field which was not irrigated. And here you see the information that we have about well, the precipitation in blue, and you see the real dry summers, which also a lot of evapotranspiration in green, and the irrigation periods, which are typically the growing season, and you see how much water has been transferred to the field. So this is the irrigated volume of water, and you can see the really dry summers, which a lot of demand for this water. But of course, we also pose ourselves questions. So what will happen in these type of systems with contaminants of emerging concern? So the effluent is coming in the saturated zone. There will be transformation, both anaerobic, but also, of course, aerobic transformation. There will be absorption. There can be uptake by the crops. There can also be leaching to groundwaters, and of course to surface waters. And all these can pose exposure routes to both humans, livestock, but also, of course, the biota in the environment. So we want to know more of the system, and we are doing a lot of measurements with non-target high-resolution mass spectrometry, but also with target high-resolution mass spectrometry. And we take samples from the crops. Here you see Dominique with these mice plants. We take samples from high in the soil, but also very deep in the soil from the surface water, so that we can really better understand the fate of the substances. I cannot show data yet because they are still in progress for the analysis, but we will also analyze them in these kind of PMOC classes. So we will discern the more persistent and mobile chemicals from the less persistent and less mobile chemicals, and you see a whole lot of chemicals are being analyzed. But again, the results are yet to come. What we already did publish is a kind of calculation. How can this reuse shift the imbalance in these dry years? Because in these dry years there is really this demand for water, and what can how can sewage treatment plants help to shift the imbalance? And here you see the Netherlands in a dry year. So this is the water demand in a dry year. This is the water demand in an average year. These are all these black dots are the sewage treatment plants. And what we did is we calculated, well, how can this sewage treatment plant effluent help to satisfy the demand? Well, in several, in fact, areas. So we calculated this for buffers up to 5 kilometers, because of course this water then has to be transported. And you can see here that in a dry year, up to 70% of the demand within this 5 kilometer buffer zone around the sewage treatment plant. So we knew all the agricultural crops and well, the agricultural fields here. And in an average year, it can satisfy up to 25% of the demand. Of course, when we have smaller buffers, a much higher percentage of the demand within these buffers can be satisfied. There is, especially in dry years, less remaining STP effluent after the subsurface or irrigation, which then also poses the question, well, how does this influence the ecological quality of the little streams in these areas, which normally are, especially in dry years, filled for up to a high percent with effluent. There we had a lot of alarms, in fact, a lot of press releases also these last 3 years of dry summers. So very widely in the Netherlands now we see the necessity not only for an energy transition but also for a water transition. Of course, historically we are very good in discharging the water, so bringing it as fast as possible to the sea, but we see now the necessity to retain this much better. And that's why we are currently starting a new large project with about 13 PhDs and 6 postdocs on key technologies, really to solve, to help this freshwater stressed delta. And what we will do is we will look at all types of possible sources to be reused. We will do this by digital water distribution modeling. So where are the demands and where are the offers of all waters to be reused? Of course, again, we will look at risk assessment in these circular systems. There will be 2 PhDs and a postdoc working here. We will also look, do we need to treat the water before this reuse better? Because in this example I just shown in Haaksbergen, there's no additional treatment compared to the normal treatment that's done by sewage treatment effluent, which, well, it might be much better to use, for example, active carbon or ozone, to make sure that the water quality is fit for purpose. We will also look at the governance questions there, and we will demonstrate this in several areas. And with this, we will really come to this, like compared to the energy grids, we will come to an optimization of digital water grids to connect these available sources for reuse and the demands. And we will apply this in several parts of the Netherlands. Here you see the precipitation deficit. We will have cases in the area around Amsterdam, where I'm working, and where we have a lot of problems also with salt intrusion. We have also this problem in the Zeeuws-Vlaanderen and Zuid-Holland, where we have a lot of greeneries. But of course, we have also lots of problems in the higher sandy soils, and we will make, in fact, intrusion possibilities for surface water to better recharge the groundwaters. And that was my small contribution for today, and I want to thank the funders and, of course, the audience for listening, and we will discuss later on.
Yes, we will discuss later on. Thank you for your contribution and for introducing, for me, the first time, the concept of water transition. We will move on to Benny to give his opening remarks.
Thank you very much, Marlene. Do you see my screen? Great. Thank you very much for the introduction. So it's really a pleasure for me to share with you the current situation in Israel as an example or as a case study to water scarcity and the solution for water scarcity in Middle Eastern countries suffering from water scarcity, of course. So just a couple of figures about Israel. Israel is quite a small country, and by the way, in terms of population density, it's very similar to the Netherlands. However, it's very different from Netherlands in terms of climatic conditions and water availability. And as you can see, the total water consumption in Israel is about 2.2 billion cubic meter per year. The urban water consumption has been decreased in recent years mainly due to education and public awareness to about 90 cubic meters per year per capita. However, still the agricultural sector in Israel is consuming a large portion of water in Israel, about 54% currently of the total water consumption. And I will focus on that because that is a game changer in our region. In terms of precipitation or climatic condition, we can view Israel, or half of Israel is a desert-like, that the annual rainfall is less than 200 millimeters per year, and only the central part of Israel and the north part of Israel are richer in water. So we have about 500, 600 millimeters in annual rain. So that's put us in a situation of a severe water condition or constant water scarcity, and we need to find additional source of water in order to provide enough potable water for the population, and of course enough water for the agricultural sector. So looking at trends in Israel, starting from, in this figure, it's starting from the 60s all the way what is predicted to 2050. So under this absolute water scarcity, two new sources of water has been introduced. One of them is the desalinized seawater, and the second one, which is the topic of today, is the reclaimed or treated wastewater that is being used as irrigation water. So treated wastewater has been introduced to the system mainly during the 90s, and you can see here that from that point, more or less, more and more treated wastewater is being used, and it's being used as irrigation water, but that was not enough to meet the demand of the agricultural sector and the municipalities. Therefore, around 2010, about 10 years ago, 11 years ago, we started to desalinize seawater, and currently about 75% of the drinking water in Israel is desalinized seawater. So this is the proportion currently in Israel. So the natural water resources are quite small as compared to what was in the past. That was the only available water resources. And in the past, what is predicted for the future, we will rely on desalination. That is the main source of water or drinking water. But let's look at trends, and we can see that in this graph I'm showing you the water consumption by the three main different sectors in Israel, starting from the early 60s all the way to today. So back in the 60s, the agricultural sector was using 80% or even more than 80% of the total water consumption in Israel. And that has been reduced to 54% currently. And by doing that, still the agricultural production has been increased dramatically, meaning that the water use efficiency has been increased by a factor of 5 or 6 during that period. And the fact that the agricultural sector is using less water is providing more water for the municipalities, because the population increase in Israel is quite high. So it's about 9-point-something million today. It's about 10 times higher than what was back in the 60s. So therefore, there is a need for potable water in the system. But that's not the whole story. The whole story about the Israeli agricultural sector is not only the amount of water, but also the type of water that is being used by the agricultural sector. And you can see that in this graph. So in average, going all the way from the 60s all the way to about today, the agricultural water consumption is about 1 billion, 1.2 billion cubic meter, quite steady between years. However, the type of water is totally different. While in the beginning of, or in the 60s, 70s, most of the water that has been used by the agricultural sector was fresh water, high quality tap water. However, due to population increase and by a higher demand by the municipalities, and by constructing more and more wastewater treatment plant, and by improving the wastewater treatment, the state has forced the farmers to use reclaimed wastewater as opposed to potable water. And currently about 50% of the irrigation water in Israel is reclaimed wastewater. So there is no question here whether we need that or not. It's a must. It's a must for the Israeli agricultural sector, and not only the Israeli agricultural sector, it's also the Jordanian, the Egyptian, the Syrian, the Lebanese agricultural sector. They are all relying on reclaimed, treated wastewater as an important source of water for irrigation. This is a must, it's not a question. The quality is an issue that we will discuss later on. So in terms of quality, here you can see the Israeli parameters are a bit different and much more strict than the parameters that are used or suggested by the WHO or used by the EU. And I'm listing here in the left side only a part of the quality parameters that the wastewater should be met in order to be used as irrigation water. And the quality of the irrigation water, or the quality of the reclaimed wastewater, is divided to three main categories. And I will start with the bottom one, the low quality. If the wastewater treatment plant is not meeting the quality for irrigation, the water cannot use for irrigation. So it's not only the treatment, it's the quality of the treatment. If the wastewater treatment plant is meeting what we call 2030, meaning the BOD of 20 and TSS of 30 and other quality parameters, the water can be used for irrigation. However, it's limited only to irrigate non-edible crops. It's limited to about 60 days residence time in a reservoir. It's limited to the fact that it must be chlorinated before application. And it cannot be used using spraying. It can be used only in drip irrigation and preferably under surface drip irrigation. However, if the wastewater treatment plant is producing high quality water, what we call the quality for unlimited irrigation, meaning that the water can be used to irrigate all types of crops by all types of techniques. And that is really great, and about 45% of the treated wastewater in Israel is meeting the high quality, and about 50% is meeting the medium quality. But the main issue here is that we are producing a new source of water, but that new source of water is coming with some negative aspects. And I listed here only some of the negative aspects, like increasing salinity, the presence of toxic elements, changing in the sodicity of the soils. Soils are becoming water repellent. There are problems with drippers that are being clogged, and there are some emerging issues, and those are the stuff that we are working on, is introduction of active pharmaceuticals and personal care products to the agricultural system. So I will summarize with that slide, just showing that we as a society are using medication on a daily basis. Those medications are being excreted from our body every day, and they are being collected to the sewage system. In Israel, about 97% of the effluents are being treated. Great. However, the current treatment process is not really removing all pharmaceuticals from the system. And about 85% of the treated effluents that are meeting the guidelines and the quality are being introduced to the agricultural environment, meaning that we are introducing constantly pharmaceuticals, personal care products to the agricultural system. So as a soil chemist, environmental chemist, we are focusing on the agricultural sector, understanding the processes and the fate in the soils, and understanding whether those contaminants of emerging concerns can be reintroduced to the food chain and be found later on either in the same human being that excreted the same drug, that is less of concern, but to other people that are not supposed to be exposed to drugs, and this is what we are doing. So exposure is there, no doubt about that, and the question is, what is the risk that is associated with that? So I will stop here, and I will be more than happy to elaborate more and answer questions later on. Thank you very much.
Thank you, Benny, for giving us perspective from Israel, a completely different situation than in Sweden, I would say, in many ways. Last, we have Anders. Welcome.
Anders, you're muted.
Thank you very much, Benny. So it's okay now? Thanks. And thank you very much, Marlene, and thank you for inviting me to this panel. And thanks also to Annemarie and Benny for your excellent presentations. Now I'm going to switch subject a little bit from the water in the wastewater as the resource to more focusing on the nutrients and organic matter in the wastewater as a resource, and how it can be used and the possibilities and challenges. Let's see. I'm trying to switch like that. Okay, good. Yes. What we can say in this picture, you can see, of course, the toilet and an agriculture field, and in this toilet you have a very non-scientific abbreviation, everything that is needed. You have the carbon, and you have the macro and the micronutrients, and they, in a sustainable society, we have to find ways where we can, in a safe way, recycle as many of these as possible, and using a different kind of systems, everything from the conventional system, wastewater system, and use of sludge, to using a conventional wastewater system, but to use systems where you can process the sludge via biochar or ashes, and recycle at least phosphorus, sometimes more of the resources, to a sorting system with separated toilet water and grey water, where you can where you can have, in this case, you can have the possibility to recycle most of these macro and micronutrients and also the carbon, as shown in the headline here. Other systems, when we process the sludge into ash or biochar, you can possibly use a few of them, and with the sludge you can use a lot of them, but not potassium, which is not we do not add the potassium, and the nitrogen is not going into sludge in a very big ratio. And also using these different kinds of systems, you also come into different challenges with the pollutants of non-wanted substances. So with this slide, I just would like to show you the resources of wastewater. Of course, we have waterworks, and we have the distribution of treatment of drinking water. We have the collection of wastewater, and we have the wastewater treatment works. There we produce biogas, and we can deliver heat back and the biogas back to the city. But we also would like to not only delivering back the treated wastewater to nature, but also being able to bring it back to agriculture where there's need, and the same thing, of course, with the nutrients. And the main challenge, you have already mentioned that in your Annemarie and Benny, in your presentations, we have the unwanted pollutants, and I would like to especially focus on the persistent pollutants, which if we add them to the wastewater system, we will not be very good in degrading them in the wastewater treatment works. So they will either go to the receiving waters, to the right, or to the left, to the agriculture field. And this is why we have to really work with in many different ways with control at source of these pollutants. I will soon come back to possibilities and a system which is called Reebok, which we work with in Sweden. First, I would like to go up to the European level, and the Green Deal of the European Commission, which is up and running now, and it was introduced by the new European Commission in the autumn of 2019. And this is the main aim of the Green Deal is to transforming the EU's economy for a sustainable future and leave no one behind. And in many of these policy areas, you can find the circular economy approach and the zero pollution ambition. And this is really exciting in a way it has never been done before by the European Commission. And these are the policy areas, and I will expand the flower. And there you have the different strategies, which are now almost ready, most of them. And you have a good political discussion between the Council of Ministers and the European Parliament on these. And the next step is to implement legislation under these strategies, and that is also ongoing. And as you can see, I've done a red ring around the ones which are in focus for the circular economy approach, and therefore also what we talk about at today's subject. So going back to Sweden, and how we have tried to work with the use of resources in wastewater when looking into carbon and nutrients. We have used the EU, the waste hierarchy, where we at the highest level have the prevention of contaminants and control of sources. Also, it's always the basis for a circular economy. The next step is that if we have enough quality, we could recycle organic matter and nutrients through the Reebok Certification system regarding sludge, and that is in most cases not possible. Then if we cannot reach the quality, or there's no suitable farmland at reasonable distances in a long country as Sweden, then we can go to next step, recycling, where at least phosphorus should be recycled. And many thanks if we also, it's a great advantage if also nitrogen and carbon could at least be recycled. And when that is not possible, the sludge could be, and the residuals could be used for landscaping if it's of the right quality. And the last step, priority 4, is incineration only, when we only have energy recovered. And of course, we have also the disposal step, and that is forbidden in Sweden and together with many other European countries. So the Reebok certification and the aims is to be a driving force to further improvement of the incoming wastewater, what we call the control at source or upstream work, and open and transparent information, and also to secure that the sludge is produced according to the regulations in the certification system. And it's called Reebok, Renare Vatten, Bättre Kretslopp, that's cleaner water, better recycling in the byline, and it's operated by us, the Swedish Water Wastewater Association, the Federation of Swedish Farmers, the Swedish Food Federation, and in close cooperation with Swedish EPA. And up to now, 5 million persons, 50% of the Swedes are connected to a Reebok certified plant. And today, 40% almost of the sludge is used in agriculture. Only 3/4 from Reebok. We are not satisfied at all that sludge is still used in Sweden, not fulfilling the Reebok certification, but only the Swedish old legislation. The focus in Reebok is to, in a very long-term goal, it's more like a vision that the incoming wastewater should have a level of metal and organic compounds, which does not exceed what we find in water closets. And the upstream work, the reduction of cadmium should be done in a way that we have the same cadmium, the same ratio of new cadmium phosphorus as the best mineral fertilizer on the Swedish market. And then we follow 60 metals and elements, mapping and monitoring, and they are not allowed to double the soil concentration in less than 500 years. The one which we have problems with now is mercury and even more silver from antibacterial from sportswear using antibacterial silver. And then, of course, organic substances. There we do not measure them all, but here we put the main emphasis on all industries connected to a municipal plant and a Reebok plant. They have to follow the lists of the Swedish Chemicals Agency PRIO guide and the Chemsex SIN list. And this is the first year when they have all the PFAS on board. So now there are 7,400 substances, and they are mapped and they have to be phased out for an industry to be able to be still connected to Reebok. Then a few things like traceability and GIS maps, digital maps, salmonella-free and third-party audits is also in the among the requirements of Reebok. So we think we have come quite a long way, but of course there are always challenges with some of the substances used in households. So we are really working to have even stronger chemicals legislation to be able to be one part of the in the circular economy. So thank you very much.
Thank you, Anders. I would like to start by just reminding the audience to post questions in the Q&A at the bottom of your screen. But before we take on those questions, we are going to have a short discussion among the four of us. Thank you all three for sharing your experiences from your respective region. I find this topic really interesting. Reuse of wastewater resources is for me key in a circular economy. But just like recycling of other materials, such as plastics, and reality is really complex, and there's like a mixture of science, technological advances, socioeconomic factors, political factors, and all that influencing the decisions. And I would like to start with in that end. So, as I understand it, the use of sludge on agricultural land differs between countries, and maybe also when it comes to reuse of wastewater. And at least in Sweden, there has been a discussion whether it's a good idea or not to put sludge on agricultural land, considering the potential toxic effects on humans and the environment. And I was wondering if there's a similar discussion also in other countries regarding wastewater reuse of wastewater resources. And also, would you say that this discussion concerns the available scientific evidence, or has it more to do with policy? Like, are we debating science, or are we having different policy ideas? And we can start with Anders and then move on to Annemarie and Benny and talk about the situation in Israel and the Netherlands.
Thank you very much, Marlene. That is really it's a good question to be discussed. I think when we look, there are several layers in the discussion. I think we have both the discussion on all the chemicals which are used in society, what we use day by day on our skins and having in our homes, when we really have contact with different kinds of chemicals, and also to the science on what is degraded in soil, what can be taken up by the crops. I think we have science in also that doesn't make it less complex, but in several steps. But I think it's really good to have a discussion with there's so much in between black and white, and there are many gray zones. And from our side, we really promote a lot of different methods. I don't think that sludge by itself can be. Maybe we will be down to 20%. Of use. The rest of the sludge has to be processed in one way or another, where we unfortunately will not be able to bring back all the nutrients and maybe carbon. So we are really hoping for in new exploited areas in Sweden that we have these sorting systems of wastewater. That could be one way to be able to have a circular economy with more macro and micronutrients and less pollutants. Of course, we will have the pharmaceuticals there, but I think that is one way to go.
Thank you. Annemarie, do you want to add a perspective from Netherlands?
Yeah, so at the moment, the reuse of sludge is not allowed in the Netherlands, so the sludge is burned. It can be reused also for biogas, for example, so this is relatively low at the reuse scale. It's being discussed if this should change. It's not used because of possible health risk, especially pathogens. But we are also aware that by not reusing, of course, we don't make, it's not good for the carbon and the nitrogen and the phosphorus cycle. So we are looking into alternatives there. We do, so there's also not a lot of intentional reuse of wastewater. So the example that I gave was the sole reuse, used to be the sole reuse of wastewater for a long time. But we see that we need this water transition. We need to capture the water. We need to make use of our wastewaters in a better way. And so that's why, for example, this large Aqua Connect project was funded. I think it's good to have the communication with the citizens, because you don't want this yuck factor. We had in Australia this reused reclaimed wastewater for drinking water. In other countries, it was introduced well, for example, in Belgium for drinking water, no problem. But in Australia, a big controversy, and the reclaim facilities were not used for a long time because of this yuck factor. So I think it's very good to make sure that it's healthy and to do the research and to communicate on this research so that people get involved into this. In the end, I think we should be able to reuse it because we need it. We know we are going to go to more closed circles, but we also will introduce technology in there to make it safe.
Thank you, Benny.
Of course, the situation in Israel is a bit different from the situation in Europe or Northern Europe. So here we are using biosolids as organic amendments for agriculture. It's been used not as a liquid biosolids like it is used in the States or has been used in Germany. It's used as Class A biosolids or mainly composted biosolids. So in terms of pathogen, it's pathogen free. And it's a very important source of organic matter to the soils. And the soils in our region are poor in organic matter, so additional of organic matter to the soil is a key factor of increasing yield, increasing water capacity, and providing fertilizers or natural fertilizers to the agricultural system. So in that respect, we are using that. And another quite interesting issue about biosolids or composted biosolids is, as Andreas was saying, they can introduce, for instance, micropollutants or pharmaceuticals to the agricultural environment. And this is done, and this is true. But on the other hand, biosolids as natural organic matter, they can be used also as a sink for pharmaceuticals and personal care products that are being introduced with irrigation water. And what we have found that in soils that were irrigated with reclaimed wastewater, but were amended also with biosolids, the amount of pharmaceuticals that have been taken up by the crops is lower than compared to the similar plots that were only irrigated with reclaimed wastewater with no application of biosolids. So in that respect, application of biosolids is really decreasing the risk, at least for pharmaceuticals and personal care products in the agricultural system.
Interesting, and I think that addresses the next question I was going to ask. So the widespread use of this reclaimed wastewater resources on agricultural land could result in these emissions of chemicals. And this emission is to a wide range of soil types, it's to a wide range of topographical conditions and climate conditions. And with the types and the amounts of chemicals in these resources varying over time, over space, how should these complications, all of which have large implications on the fate and the transport of the emitted chemicals, be addressed from a regulatory perspective, do you think? And I would like to discuss both upstream and downstream regulatory aspects. Do you want to start, Benny, or?
Yeah, it's a pleasure. Thank you very much for the question. I think just a second, there is a jet fighter above my house, so it's a bit noisy here, but it's okay. Let me talk about downstream. What we have found in our recent studies that at least the Israeli population that we are using as a case study is being exposed to pharmaceuticals, a personal care product that they were not consuming or taking. So we are sure that when we are using reclaimed wastewater containing pharmaceuticals and personal care products, some of them, the ones that are more persistent, the ones that are not being degraded in the soils, the ones that can be taken out by plants, the ones that are not being transformed by the plants can end up in our human body. That is known evidence so far. The question is the regulatory aspect that must be based on a risk. And currently, I don't think that we as a society or the scientific society have enough information about the possible risk to a mixture of chemicals that are being emitted to the environment because of the use of reclaimed wastewater for irrigation. So in my view, there is a need for modeling, further study, and also clinical studies that will evaluate the effect of chronic exposure to a mixture of pharmaceuticals and personal care products, and maybe PFAS and others that are being introduced into the food chain by the use of reclaimed wastewater. Upstream, we have to make sure that we have regulation that will prevent some of those contaminants to enter the system, or we have enough better technology to remove them before they are introduced to the agricultural sector. So in my view, we need to work on both ends, scientific and regulatory, looking at mixtures of chemicals rather than single one, and that's the way to go. And there is a way to go till we understand the full picture or get the idea about the full picture here.
Annemarie, do you want to add something?
I think we should not forget that because that we have a lot of unintentional reuse already. So we are also in the current system, we are pumping water to spray the lands from our surface water, and our surface water are often, at least in the Netherlands, sometimes for 50% filled by effluent, especially in dry periods. So I agree with Benny, we should focus both on less hazardous, less persistent chemicals. We should avoid emissions where possible, so much more closed loops in production system, much more technologies where the chemicals will enter into environment, and of course rules for reuse, but don't prevent the reuse, because I think we need the materials in there. Yeah, more knowledge, more legislation, also to drive the measures to be taken upstairs. So I think it is the balance, but these measures, zeg maar standards downstream can also steer more precautionary action upstream.
And Anders?
So a few things more. Most things have been said, I think. But a key word for us is persistency, where we know that metals are very easy and cheap to analyze. So we can analyze these 60 elements everywhere, and metals, which we do in Reebok. But on organics, it's a totally other cup of tea, of course, where we really, the most efficient way is to have these lists to stop the discharge from industries. If they use these chemicals, they are not allowed to be connected to these Reebok plants. And as Annemarie told you, we have all the almost 5,000 PFAS there, and 7,400 from these lists. And then we can at least stop the peaks, which could come from the industries. We cannot stop what is used in our homes, but I think it's an important start. And we will also influence now when the European Commission is revising the new Urban Wastewater Treatment Directive, that if we are going to promote circular economy, then industries cannot be connected in every way to the wastewater treatment plants in the future.
Okay. I would like to end this discussion with the and before we start the Q&A, to talk about what we can learn from each other, because these are two different fields, wastewater reuse and reuse of sludge. What can you learn from each other? Who wants to go first?
Please, Benny.
Okay. Anders, go ahead.
So what I was going to say is that we actually, the last 6 months, have started to look into how can we use the Reebok certification system, which is really a system for the control at source. And also we have a model for sludge to be used, and when it can be used in agriculture. We would like to develop a model for irrigation of treated wastewater, where you have to be certified in your control at source work, and then you can also be having this module for treated wastewater for irrigation. That would be fantastic, exciting.
Maybe I will add something, more on a philosophical aspect. I think that I don't know how we can learn from each other, but it's a must that we learn from each other, because we need to look at the food trade globally. So the fact that we are using reclaimed wastewater in Israel, and reclaimed wastewater is being used in Spain or other places, it's not only a local problem or a local issue, because produce are being exported to every country in Europe. So the fact that our regulation is your regulation and vice versa. So we need to make sure that we have guidelines not only on the local, state, and even not on only on European level. We have to have some kind of a global guidelines how to use reclaimed wastewater, how to use biosolids, whether it's allowed or not, based on local conditions. But some guidelines must be there, and we have to think not only about the developed countries, but also on the undeveloped countries or developing countries where untreated wastewater is being used, where biosolids with no treatment is being applied and produced are exported to developed countries. So we need to think globally in that respect, and we need to do that the sooner the better.
I agree very much with that. I was wondering, Anders, you said industry isn't allowed to make use of sewage treatment plants when they emit, but this monitoring is, well, how do you do this monitoring? Because I think we should have post the burden of the monitoring to the producer, and he or she should give the evidence that there is no emission. In the Netherlands, we have emission by industrial wastewater treatment plants, but also many small industries make use of municipal wastewater treatment plants. And the monitoring of this and also the registration of all these substances that they emit is still rather poorly developed, I would say. And I think there are big things to be moved there. But the burden for this should come to the industry itself, so that the industry also can say, well, I'm acting safe and responsible. It's also in their interest. So,
Marlene, may I just comment on Annemarie's question?
Absolutely.
Yes, it's it's absolutely right that it's on the polluters pays principle, and it's really in focus, and also that pollutants should be controlled at source, which is also in the European Commission's treaty, European Union's treaty. What we are doing is that we can, locally, the wastewater treatment plants, together with the local environmental authority, they are demanding the lists of chemicals used by each industry. And so the resources is not really used to check what is in the effluent from the industry. It's more to check what is in the influent. So these lists of chemicals, which can be hundreds of them, but then the cast numbers are checked against these lists of 7,400 substances. That's the way it's done. And then they have, of course, a phasing out period. And if they are used, they can only be internal circulation systems.
Thank you. The first question from the audience concerned the goal conflict between carbon neutral and a toxic-free environment. So if we use more advanced treatment technologies, they will be more energy intense. How do we argue for that when we also need to save the climate? And I think this connects to something that we discussed before this seminar. So how do we convince decision makers to invest in these type of technologies so that we can reach the goal of a non-toxic environment? Who wants to go first? Annemarie?
Yeah, I can go first. I think, you could better safe than sorry, or safety first. So we need circularity, but it can be really hampered by the idea that this circularity is not safe. So I think it's mandatory to reach circularity to do it in a safe way. We can't do it otherwise. So I think it shouldn't be. It is not, in fact, a conflict. It's a requirement, a mandatory requirement, and it should be really aligned. It's not a choice. We can only do it safe.
I totally agree with Annemarie. In that case, we have to combine the two ends, you know, the safety and the circular economy. It's not this one way or another. We have to combine the two. So we have to make sure that we are thinking circular economy, and we are investing enough in technology to make sure that the product, in that case, either biosolids or effluents, are safe for the users and all users, not only the agricultural sector, but also animals or humans in the end of the food chain.
Yes, it's really a challenge, and the only way forward if we would like to, which we would like to, change the concept of wastewater treatment plant to a resource treatment plant, then we have to do it in a way which is safe, and if we also would like to use the carbon in the resources, what kind of safe ways can we use for carbon sequestration, so the carbon in the resource from the wastewater treatment plant can still be used, because if we incinerate, it is lost. Maybe we have too many pollutants if it's not incinerated. What can biochar do? Is that something in between? So it's an exciting field.
Next question from the audience is concerned quality criteria. So do you think there should be quality criteria addressing micropollutants in effluents introduced when the EU Urban Wastewater Treatment Directive is revised? And what kind of criteria should that be according to your opinion?
So maybe I will go first here. So I think that there is a must for quality criteria, if depending on the goal of the reclaimed wastewater, whether they are being used for irrigation or whether they are being discharged to streams and lakes, surface water. So criteria must be there, but I would suggest a tailor-made criteria case by case, meaning that we can have a criteria of zero pollution, meaning that all chemicals must be removed before water is being charged to the system. But maybe we are wasting too much energy and efforts on removing everything that will naturally degrade in the system itself. So we have to know the types of chemicals that are persistent in the environment and during the whole food chain, and target them later on in terms of criteria and quality parameters, and making sure that technology is being there to remove those pollutants of emerging concerns rather than removing everything from the water. So this is my view about that topic.
I would think that they are thinking about introducing more criteria than there are now, so I think that's wise. Of course, you can think about criteria fit for purpose, so depending on the purpose. I don't think it should be really case by case, because then there will be a lot of research demanded each time for each reuse case. So I would think about more generalization. And of course, I think we have to dispute, well, if we want to be as multiple, as much reuse possible, the various types of reuse possible, then we should go more stringent than when you say, oh, for this case of reuse, this can be allowed, and for that case of reuse, that can be allowed. And stringency is always good on the one hand, because then it gives a pressure upstream in the upstream use of chemicals, but at the other hand, it might lead to overdo of technology implementation. So we have to seek for the right balance there, and I don't think we already know what is the optimum there.
Mm-hmm. I really like this discussion that reuse of wastewater is, we always reuse wastewater. Either we have it for irrigation or we leave it back to the receiving waters, because it's always reused. We cannot just take it away. And talking further on that, I think that there is a need for a demand on watching on the persistent organic chemicals and using the Water Framework Directive, which we already have in place in Europe, and having the standards for good chemical standard, and we will now soon, I think, add a few pharmaceuticals there, as diclofenac, for instance, and then from that on we will have we will know where we have to introduce advanced treatment. That is when we cannot fulfill good chemical standard if we are talking about leaving back the water to surface waters. And but it will never be possible to, I think, even though I'm an engineer and very technical positivist, to install advanced treatment in all 1,700 Swedish wastewater treatment plants. We can do this in 50 or 100, and then we have covered maybe 70-80% of the population, and then we have only covered the one which takes care of more than 50,000 persons. So the smaller one, we always have to work control at source, wise use of pharmaceuticals, and then when it's needed and have a good prioritization, we need also advanced treatment.
Thank you. We can continue with this question to you, Anders. The wastewater treatment plants connected to REVAC needs to manage chemicals on the SIN list and the PRIO list. Have you seen any effects of this? Are there any analysis being done to monitor whether this is followed?
There is a check together with the local environmental authority. So of course it could be legal breaks by the connected industries, but not showing the right lists. So and the checks are quite few, I have to say, but it could be sure and a good area of research projects following up of these of the wastewater from in to wastewater treatment plants, and checking after the connection, are they using these are they using these substances of high concern, even though they are not saying they're using them, but they are showing all the official lists which they have to have due to the Environmental Act in Sweden. So we should do a few tests, but haven't done it yet.
Maybe this can be some kind of collaboration between Stockholm University and you on this.
Yes,
I see a potential research
that would be
need. Yeah. Okay, we have a question here. How is the exposure to persistent chemicals via potable water in relation to via solid food? In drinking water, many more persistent chemicals can be detected than in solid food, at least in Sweden. That's the question.
I think this really depends on the chemical in question. So for the rather hydrophobic chemicals, you often see that food is the majority of exposure. For very volatile chemicals, inhalation contributes much to the exposure. For the rather mobile chemicals, water can can attribute much to the exposure. When we derive quality limits for drinking water, we typically assume 10 or 20% of the total exposure coming from drinking water, but it can be much higher for the mobile compounds. So you can't answer this generically. It really depends on the physical chemical characteristics of the chemical.
And we are really looking forward now to the use of not only the PBT criteria, but also PMT when we are using the chemicals regulation REACH, which is to identify the substances of very high concern. That's a good step forward.
Just one issue to add to what has been said before. When we are looking about agricultural produce, we have to remember the water use efficiency by plants, which is a factor of 100 or sometimes 500, meaning that to produce 1 gram of biomass, we need 500 grams of water. And in that respect, if the chemicals are persistent, so they are being accumulated in the biomass, and therefore eating 500 grams of lettuce is much more risky than drinking 500 ml of water, whatever chemicals are there. So we have to think about that as well. And again, I'm talking only about chemicals that can be taken up and can be accumulated in plants. And in that case, the risk from consuming produce is much higher than drinking water.
Benny, we have a question to you, clarification from your presentation. Did I understand correctly that potential hazardous substances are not measured in the wastewater used in agriculture?
They are measured. However, and the regulation for heavy metals and pathogens and chemicals in general are there. Inorganics are being measured on a regular basis, and it's part of the regulation. What is not being measured regularly are the organics, and mainly the pharmaceuticals and personal care products, PFAS and other emerging pollutants of emerging concerns. They are not being regulated and or being measured regularly. And that is the next step, in my view, to pose some regulation about that. But all inorganics are being measured.
Thank you. Going through the list here, see if we can I think maybe the last question here. In terms of human health impacts associated with wastewater reuse, should we be more concerned around direct consumption, exposure to pharmaceuticals in crops, or the risks associated with the proliferation of antimicrobial resistance in soil plant systems?
Well, they are connected now. So it's not the one without the other. So if we use pharmaceuticals or antimicrobials, we are also introducing this antimicrobial resistance, and it's both to worry about. We know, of course, that for the in general for the pharmaceuticals, the chemicals. The exposure for individual chemicals is much lower than daily doses which are prescribed. But we have this question of mixture, and we know for human health that there are really human health problems connected to AMR, so that we can't cure certain diseases with certain antimicrobials anymore. So, but we also know that for the pharmaceuticals, we do have all these ecotoxicological effects also for the single compound. So it's both problematic, but it's very much connected, I would say.
Thank you. I changed my mind. I want to have one last question. When we talk about monitoring, who pays, the producer or the user?
I would say the producer, but he will send the bill to the user.
I totally agree with you.
Okay, I think that was all that we had for today. It's 4:15, and it's time to end this discussion. Thank you all for participating. Thank you to the participants who asked questions or just participating by listening. Keep coming back to our seminars. We have new interesting topics coming up. So have a great day. Bye bye.
Thank you. Bye.
Bye bye. Thank you. Thank you all.